Have you ever wondered why the true orbital period of a planet around the Sun disagrees with observations? Astronomers strictly separate the true sidereal period of revolution and the apparent synodic period between identical configurations. A special equation of synodic motion links these two important quantities with the orbital race of our Earth. This mathematical relationship allows scientists to easily calculate the precise motion trajectories of any planets in our system.
Let's begin today with what is a truly fundamental problem in observational astronomy. How do you determine the true orbital period of a planet? Now, the challenge here is that our observatory, our point of view from planet Earth, is itself constantly in motion. Imagine you're trying to time a runner on an adjacent track, but you're also running. See the problem? This complication of relative motion is precisely the issue we are going to solve.
All right, here's our roadmap. We're going to start by framing the problem from our moving point of view. Then, we'll need to define two absolutely critical concepts, the sidereal and synodic periods. After that, we'll get into the mathematics and derive the relationship between them. And finally, we'll use that math to see what it tells us about the real clockwork of our solar system.
So, let's dive right in. First, we have to really appreciate the complexity of observing the universe from a moving platform. This, right here, is the central question. You might think it's simple. Let's say we watch Mars, and we just time how long it takes to get back to the same spot in our night sky. Is that a Martian year? Well, the answer is a definitive no, because during the entire time Mars was moving along its orbit, so were we.
You see, the time between two identical alignments, say from one opposition, where Earth is perfectly positioned between the Sun and Mars, to the very next one, that's not Mars's actual orbital period. What we're observing is a composite, a blend of Mars's motion and our own. To find the truth, we have to find a way to mathematically untangle those two separate motions.
And to do that untangling, we need to be very precise with our language. This brings us to a crucial distinction between two different ways of thinking about a planet's period.
On one hand, we have the sidereal period, which we'll label with a capital T. You can think of this as the true period. It's the actual time it takes a planet to go once around the Sun, measured against the backdrop of distant fixed stars. On the other hand, we have the synodic period, labeled S. This is the observed period, the time we actually measure from Earth between two identical lineups.
So let's be very clear about the sidereal period. This is the planet's actual year. The racetrack analogy works perfectly here. Imagine a car completing one full lap. The sidereal period is the time on the stopwatch from the start-finish line all the way around and back to that same line, with the stadium itself, the distant stars, as your fixed reference.
Now, the synodic period is completely different. It isn't about one lap. It's all about alignment. It's the time it takes for the Sun, the Earth, and another planet to get back into the same geometric arrangement. So the time from one opposition to the next opposition, that is the synodic period. It's the only one we can directly see and time from here on Earth.
So here's the crucial point. We can observe S, the synodic period, but we want to know T, the true sidereal period. The bridge that connects what we see to what is true is the equation of synodic motion, and now we're going to derive it.
Let's consider two cases, starting with the inner planets, Mercury and Venus. Their true years are shorter than ours, meaning they orbit the Sun faster. Now think about it. For Venus to get back to the same alignment with us, it doesn't just complete its orbit. It has to go so much faster that it essentially gains one full lap on us.
To quantify this, we'll use the idea of angular velocity. It's simply the number of degrees a planet moves through its orbit each day. So a planet's angular velocity, which we'll call n, is just 360 degrees divided by its true period, t. Earth's is the same, n sub Earth. Now, for a faster inner planet, the relative speed, the rate at which it's gaining on us every single day, is simply its velocity minus our velocity.
Okay, so follow this logic. For the alignment to repeat, that inner planet needs to gain a full 360 degrees on us. So if you take the amount of angle it gains per day, and you multiply that by the total number of days in the synodic period, S, that product must equal 360. From there, we just substitute our definitions of angular velocity into the equation, and with a little bit of algebra, we divide the whole thing by 360, and we arrive at this beautifully simple relationship. 1 over S equals 1 over T minus 1 over T sub Earth.
Now what about the outer planets, Mars, Jupiter, and so on? Their orbital periods are longer than ours, so they move more slowly. In this case, the roles are completely reversed. It's now the faster Earth on the inside track that has to do the work of lapping the slower outer planet to get back into alignment.
The logic is identical, but the terms just get swapped. The relative angular velocity, how quickly we gain on them, is now our velocity minus their velocity. It's reversed because now Earth is the one doing the lapping.
And when you run this through the exact same derivation, you get this formula. Look closely. It's almost identical to the first one, but the subtraction is reversed. It's just so elegant how the mathematics perfectly mirrors the physical dynamic of the chase.
So, with these two equations in hand, we now have the power to translate our simple, earthbound observations into the true celestial architecture. Let's see exactly how this works.
What you see in this table is the payoff. The synodic periods in the middle column, S, are the values we can directly observe and measure. We know Earth's sidereal period is 365.25 days. So for each planet, we can just plug its S value into the correct equation and solve for T, its true sidereal period. The result is nothing less than uncovering the solar system's true structure, all derived just by correcting for our own motion.
Now, something here should jump out at you. Look at the value for Mars. Its synodic period is 780 days, which is the longest of any planet on this list. So, what's the physical reason for that?
It's because Mars's orbital speed is actually quite close to our own. We're running in adjacent lanes, and we're only a little bit faster. That means it takes us a very long time, more than 2 years, to lap it and set up another opposition. And that's why these oppositions, which are the absolute best time to observe Mars, are such rare and highly anticipated events in astronomy. Now contrast that with Jupiter and Saturn. We're moving so much faster that we lap them pretty quickly, and their oppositions happen nearly every single year.
And I really can't overstate the historical importance of this. This is so much more than a mathematical exercise. It was with this exact logic, these very formulas, that Copernicus was able to calculate the sidereal periods of the planets. This provided for the first time a consistent, mathematically sound framework for the heliocentric model. And it fundamentally transformed astronomy into a predictive, quantitative science. So we're left with a final, powerful thought. By simply accounting for our own motion, by correcting our perspective, we unlocked the blueprint of the entire solar system. It's a profound reminder in all of science. Sometimes, the greatest discoveries aren't about looking further out into the cosmos, but about more accurately understanding our own point of view.
Thank you, friends. Strive for understanding and become wiser. See you soon.